who will speak about seroprevalence studies for SARS-CoV-2.
Great. Thanks, Shane. Everybody can see my screen okay? Great. Thanks very much for the invitation to present today. I'll be chatting with you a little bit about SARS-CoV-2 seroprevalence studies for immunity modeling and focusing on, data identification, interpreting findings, and their use in both transmission and statistical models. So, seroprevalence studies, of course, provide key insight into the true extent of SARS-CoV-2 infection and hence into immunity that results from infection, and are an important window into that as a result of asymptomatic infection and as a result of limited diagnostic testing availability, particularly in some countries and regions around the world. Confirmed cases considerably undercount the true extent of infection. And so serological assays, which in seroprevalence studies, which measure the prevalence of antibodies against SARS-CoV-2, are really crucial to understand the true extent of infection and our best window into the true extent of infection. And what I'll chat about with you today, it centers around three main points. First, I'll chat a little bit about identifying serosurveys using SeroTracker. Secondly, interpreting data from serosurveys and key considerations when interpreting that data or when using that data as an input into models. And then finally, a bit of some thoughts on using serosurvey data in immunity modeling, very, very briefly on transmission models, and then some of our own work on the development of statistical models focusing on seroprevalence data. So first, we'll focus on identifying serosurveys using SeroTracker, which is a dashboard and data platform for these seroprevalence studies, on how we identify data, how you can use that data, and what that data tells us. So early on in the pandemic, we realized that seroprevalence data, well, firstly, that serosurveys were being done as these one-off research studies as opposed to continuous surveillance programs. And so that there was a need for, a data aggregator to bring data from all of these studies together. And so we kicked off what is essentially a massive living systematic review of SARS-CoV-2 serosurveys, which we include, across countries, populations, languages, across published papers, preprints, government reports, and from January 1st, 2020 through to today, updating our search each week. And in our data pipeline, we try to identify these serosurveys, screen them, and as you would in a traditional systematic review, and that's yielded so far something like 2,500 seroprevalence studies that have been done in the pandemic to date across nearly 120 countries. And from each of these studies into a standardized data extraction form, we pull out, information about how that study was done, the design of the study, the characteristics of the sample, the testing algorithm used, about seroprevalence for the overall population studied, also for specific population subgroups, the immunoassay used, and so on. And we do this in duplicate and also provide human assessment of, what the quality of that data looks like. We critically appraise it. And all of this, yes, it's a living systematic review, but it also feeds our dashboard on serotracker.com, which is a data platform for these studies. I'll take you very quickly through the SeroTracker dashboard, which you can find on serotracker.com. This is the explore page of the dashboard, which shows dots which represent seroprevalence studies that have been done to date. And each of these, with each of these dots representing a seroprevalence study, you can take a click on one of these seroprevalence studies that's located where that study was done, and you can see, that this study in particular was a national seroprevalence study in Ireland that used a household sampling method from these dates to these dates and estimated a seroprevalence of 1.7% at that time, which was early mid-2020. We also provide some contextual information here. And of course, you can filter by criteria of interest on the right-hand bar here, including where that data came from, what we assessed its risk of bias to be, the population in question, and perhaps most importantly, the date that this study was done. Second, there's some graphs on the Analyze page of our website. This is the Analyze page, if it will unbreak for me here. Basically just summarizing some of the key findings across studies, including some results from some global modeling work that I'll talk about later. These are available for you to dig into at your leisure, and I'll chat about a couple of these findings in particular later on. And then finally, perhaps of most interest to the folks on this call, is data available for download, a CSV available, so you can programmatically access our data and use it in your own modeling work. Just to jump back to, oh, I've just stopped my share instead of exiting out of the SeroTracker dashboard, but I think I'm back where I was earlier now. Just want to chat a little bit about how folks have been using SeroTracker's data to inform some of their research and modeling. And so, this includes research groups who are interested in modeling the true extent of SARS-CoV-2 infection and monitoring seroprevalence, public policy groups where the SeroTracker data really does feed WHO data pipelines, and then some journalistic work as well. And one example of this, is the economists' work on excess mortality. They're interested in, cross-referencing, given what the seroprevalence is country by country, and given what we know about the infection fatality rate of COVID, what do we expect excess deaths to look like on that basis? And of course, their methodology is not just based on seroprevalence data and the IFR, but SeroTracker data does help feed the model that they have developed, and which is now used by public health NGOs to monitor the true impact of the pandemic globally and to drive funding allocation to LMICs. Now, I'm going to just share a few findings from a meta-analysis of the studies included in the systematic review. These are slightly older findings, including a search from January 1st to December 31st, 2020. We've recently rerun some of this analysis, and while I can't share the figures just yet, a lot of the key findings do remain the same. So this isn't quite as stale as it might seem from the outset. So first, there are considerable differences in seroprevalence between demographic groups. And so we do see considerable heterogeneity in seroprevalence here. And so what we've done in this analysis is that we've identified all studies that reported seroprevalence in two groups of interest. For example, say males and females. And then we calculate a prevalence ratio for each study, the seroprevalence in males divided by the seroprevalence in females, and then meta-analyze those prevalence ratios across studies. And each row on the plot shown here is the result of a separate meta-analysis. And we can see, that we see lower seroprevalence in older adults, higher seroprevalence in individuals who had close contact with with folks with COVID-19, and in healthcare workers, higher seroprevalence in Asian, Black, Indigenous individuals of minority ethnicities, and then comparable seroprevalence by sex. And these findings are recapitulated in more recent analysis. Second, we know that, of course, these populations studied influences the seroprevalence that is estimated, but also there's various study design factors which affect serosurveys and the seroprevalence estimated through these serosurveys. And so we conducted a multivariable meta-regression to identify factors that might influence seroprevalence, including both design of seroprevalence studies and the context in which those seroprevalence studies were done. And the right-hand plot shows the results from this multivariable meta-regression, which suggests that generally, of course, where we have more confirmed cases, we see a higher seroprevalence. that there are substantial residual effects of the global burden of disease region in which the serosurvey was done, and notably that the national seroprevalence studies tend to report a higher seroprevalence than local or regional seroprevalence studies, which one can consider to be likely attributable to the fact that in general, or that some of the time, regional and sublocal seroprevalence studies are done in areas where there have been outbreaks and that aren't necessarily representative of the seroprevalence in the population as a whole. Finally, just a quick glance at ascertainment. This of course data from earlier on in the pandemic, but we essentially calculated the ratio between seroprevalence and the cumulative incidence of confirmed cases in the country in which a seroprevalence study was done, doing this for all national seroprevalence studies in the general population, and seeing what that implies about ascertainment. And these numbers in the most recent analysis do go down a little bit in the general population, but the overall theme remains the same, that we are certain that confirmed cases certainly undercount the true extent of infection, and that there's substantial heterogeneity in the extent of this undercounting globally, with with quite substantial undercounting in many low and middle income countries, which is worth considering when interpreting seroprevalence data or when interpreting confirmed case data and using that data to produce global models of infection and immunity. Moving on to the next slide, now we've chatted a little bit about the seroprevalence data available through SeroTracker and what one might be able to do with or what some key findings from that data are. And in thinking about how to actually use that data, it feels important to quickly touch on some key considerations in the design and assay used in serosurveys that affect the estimates produced by those serosurveys, and that are just sort of important to think about when using serosurvey data for immunity modeling work, or when just interpreting the finding in serosurveys in a general sense. So from that same meta-analysis I was talking about earlier, we critically appraised every study in duplicate, and across these 900 studies, we found that actually over half of studies were at high or unclear risk of bias. And there were a few different things going on here, generally related to the use of questionable sampling methods, or the use of serological assays that didn't necessarily generate robust or reliable estimates of seroprevalence. And so I'll talk a little bit about what some of the drivers of this assessment were, and what are some key things to look out for when interpreting seroprevalence studies. Firstly, in terms of sampling considerations, I want to reflect a little bit on the sample frame used and how representative the sample used is. In terms of the sample frame, the key question here seems to be whether inference can be drawn from this, the sample studied in the seroprevalence study to the population of interest, the population that one is trying to estimate or understand seroprevalence within. Of course, in terms of the population studied, there have been quite a few studies of healthcare workers, but these are obviously not that useful to understand seroprevalence in the general population. Perhaps slightly more subtly, study scope matters. We talked about local and state level studies not necessarily being representative of the general population in a country as a whole. And then finally, something to consider here is timeliness. As most of these studies have been done as research studies, there is a considerable delay between when individuals are sampled and when results are made available. On the point about the way sampling is done itself, I mean, probability sampling is certainly something to look out for in direct studies of the general population, in those doing household surveys or similar. But some studies use proxy sampling frames like blood donors or residual SARA, and it's possible to do these studies quite well. Some of the studies funded by the CITF fall into this category. Some of the US blood donor and residual SARA studies done by John's colleagues at CDC certainly fall into that category. But it feels important in these sorts of studies to consider whether estimates were corrected for differences between the sample and the population, and moreover, whether there was sufficient coverage of the target population for weighting to really be enough to understand what's actually going on there. As John mentioned, blood donor studies can't tell you much about what's going on in terms of seroprevalence in children. Now, there's some more subtleties here in terms of seroprevalence studies, thinking about the assays in use and the vaccines in use together. And so, seroprevalence studies will generally either use or provide seroprevalence estimates for both anti-N antibodies, antibodies against the nucleocapsid protein, or antibodies against the spike protein. And in general, assays that detect antibodies against the spike protein tend to show a little bit more stability. These antibodies are triggered both by infection and by all vaccines currently in use globally. But on the anti-N antibody side, these are triggered by infection, but only certain vaccines. So of course, your mRNA vaccines, which use spike protein antigens, won't trigger these responses. And so it's important to understand, or to put the seroprevalence data in context to understand, say, in the Canadian or American context, where largely only anti-S or only S antigen vaccines are in use in the population, to say, okay, is the seroprevalence attributable to infection or attributable just to infection and also to vaccination? Secondly, there's some assay considerations to keep in mind here. And John touched on some of these as well earlier on. In essence, assay performance, sensitivity, and specificity matter, particularly in settings where the true seroprevalence is low and there might be quite a few false positives with a low specificity assay. But also, there appear to be considerable differences in how well different assays maintain their sensitivity in detecting past infections over time. As John also mentioned, the Abbott anti-N assay appears to see a substantial decline over time. The Roche anti-N assay much less so, and you can see considerable differences in survival of detectable antibodies post-symptom onset in individuals with confirmed COVID-19 on that right-hand side panel here. Finally, just a quick touch on using serosurvey data in immunity modeling. And so, talking briefly about transmission models, we've talked a bit already about using serosurvey data from repeated cross-sectional studies to understand the force of infection, both from repeat studies, as John talked about, from individual studies, and also potentially from household studies. So I provided a few references here that might be relevant to folks. Secondly, case ascertainment, as we saw, to take a glance at the extent of under ascertainment in case data, and potentially, if using case data to drive a transmission model, to use this to understand just how many cases have actually been missed. And then finally, using serosurvey data to just estimate the percentage of individuals who might be in the recovered compartment at the start of a model run. Now, there's a lot of challenges with this because there's not perfect correspondence between seropositivity and immunity, but the Larimore paper cited here does some really interesting things and using serosurvey data to feed transmission models, and in propagating uncertainty from seroprevalence surveys through the transmission models developed. So perhaps more of a screenshot slide with random references in here for folks who may have an interest in any of these particular topics. In the remaining time, I want to chat a little bit about some of our work to develop statistical models of seroprevalence. And really, I'll focus on here the issues in both the Canadian and the global contexts in understanding what seroprevalence looks like. Now, like I've talked about a bit in this presentation, seroprevalence studies have been done largely as research studies in the course of the COVID-19 pandemic. And because they've been done as research studies, well, it's not like you have a study available on a national level for every country for every month. And if that were the case, the job of folks looking to understand this would be much simpler, but some countries have quite a bit of data with overlapping studies using different methods. Some others have quite sparse data. Some other countries have no data altogether. And of course, there are reporting delays as a result of the fact that these are, very much done as research studies, largely and not continuous surveillance programs. And we know that both confirmed case and death data are generally reported in a much more up-to-date fashion, but that both of these are subject to considerable undercounting or underreporting bias. And so the question then arises then, is there a way to triangulate between seroprevalence data and other sources of data in order to understand the true extent of to understand what seroprevalence is in the time periods between seroprevalence studies and up to the present day when seroprevalence data isn't available, but when we have case and death data to nowcast a little bit, if you will. And what we've been thinking about to do that is to model the relationship between seroprevalence and confirmed cases and how that varies over time, and then to use ascertainment to estimate seroprevalence, and ultimately to bring deaths into the picture, but we aren't quite at that stage yet. So I'm going to chat a little bit about some of the work we've done in collaboration with the COVID-19 Immunity Task Force, with David Buckridge, with Jane, with others, to produce models of seroprevalence within the Canadian context. And so in Canada, we've got reasonably good time series of confirmed cases. We think there's some under ascertainment here, but not a ridiculous amount. And of course, we have quite regular seroprevalence data available from studies from Canadian Blood Services, Statistics Canada, so on and so forth. And so we leverage this data to estimate in a statistical model of case ascertainment and hence of seroprevalence. The model specification we have right now here is on the right. Rho GT represents the ascertainment in a certain geography, in this case, the population, and at a certain time point. And we let this extent of ascertainment, or the ratio between, the true number of infections and the number of recorded cases in that region, to vary according to the test positivity rates. And also group or province-specific slopes and intercepts on that ascertainment. And then secondly, we say that infections in a certain province and at a certain time point are equal to the number of confirmed cases times that ascertainment. And then we just take the mean seroprevalence at a certain time point to be the sum of infections all the way up from the start of the pandemic to that time point, divided by the population, and parameterize the seroprevalence with a beta distribution. And here we have the mean variance parameterization of the beta distribution with this kappa parameter that represents variance, which we just put an uninformative prior on. And we fit this model within Bayesian frame. Oh. Apologies, I think my webcam has just unplugged itself, but I think folks have me back now. We estimate these models in a unified Bayesian framework using Markov chain Monte Carlo in the statistical modeling package STAN. And some of our early results here are shown in the left panel. We see that we get the x-axis here is time. Each facet represents a different province, with AT being the Atlantic bubble represented as one province, and y-axis being seroprevalence. And we see here that we get reasonably good fit to the seroprevalence data for each province, which is shown as sort of the subtle gray points here. And so we're working on currently putting this together for the next report of the Immunity Task Force's modeling group, which we expect to make public later this month. And once we've done that, we plan to extend on this model to permit seroreversion and also to include anti-S seroprevalence estimates in a multivariable modeling framework. And also finally, to overlay potentially data on how long protection lasts after infection or after vaccination to produce models of what protection looks like in the population. Just briefly on the global context, seroprevalence data are really sparse comparatively. The quality of routine surveillance data is more poor, and there's quite a bit more heterogeneity in that there's substantial underreporting, but also heterogeneity in the extent of that underreporting country by country. And so I'll skip over some of the more crude work we've done to get at this and just briefly say that we're also working on building similar statistical models where we don't just use the test positivity rate as a predictor of ascertainment, but where we also look at various time invariant quantities like a WHO region, GDP per capita, the Global Health Surveillance Index, and also time varying quantities like the testing policy in the country at a given point in time in order to understand what's actually going on in terms of the ascertainment. So now, serosurveys do raise some key questions for immunity modeling. And briefly here, the way I view this is that serosurveys provide perhaps a blurry window, but our best window into the true extent of an infection and hence immunity attributable to infection. And so that immunity modeling can really help us turn seroprevalence data into good time series of what past infection looks like, and in turn, the extent and distribution and longevity of protection in the population. And there's various questions for immunity modeling that this raises. But I recognize that I've gone right up until 4 p.m. and with many apologies to Jane and to the organizers for not quite scoping this talk right and going through it at such a breakneck pace. I'll open the floor to any questions that may have arisen if time permits, or perhaps we can just move on to the discussion.
Thanks, Rahul. I will get Ed ready to moderate the discussion panel for this morning. And while he's getting ready, if I could ask a question about your analysis where you look at the number of infections per reported case by geographic region. Yeah, this one. So I was wondering if here you've included in the analysis the different population pyramids, like age structure pyramids that you can have in these different geographic regions on average.
This is, we haven't included that. This is a sort of top level analysis where we're just looking at seroprevalence in the population, in the general population in national studies and comparing through with the cumulative incidence of confirmed cases. It would be really interesting to compare and contrast this with an analysis that looks at, the number of that tries to assort that seroprevalence across different age groupings and looks at what that implies about the number of infections based on what we know about the age-varying infection fatality rates. I'm not sure if that answers your question, Jane.
Yeah, it does, as well as age is the population age pyramid or age structure in these different geographic regions can vary quite drastically from, having more younger and less older, or even the mean estimated lifetime for individuals in these regions, which can certainly affect the outcome of COVID-19 infection. So that's all I had a question about. So Ed, are you ready for the discussion panel?
Sure, yeah. So I guess probably if people type questions in the chat, I guess that would work the smoothest.